Let's take a look at this problem. So we have the following amount of area. So we have this x squared. And then here we have 1, 2, 3, 4, 5 of these positive x's. And then I have one of these negative ones. So that's how much area I have. And normally, here's what we do. Normally, what I would do is I would take these, split them in half, put half of them vertically, half of them horizontally, and then I would, I've never had this situation. Like, I've always had an even number. Every single problem I've given you, this has always been even, and I did that on purpose. I wanted it even because, for example, if I had 6, I could have 3 here and 3 here. If I had 4, I could have 2 here and 2 here. But what happens when I have 5? You know, I'm trying to make a square, and if I take this and put it here, that's not a square anymore. If I take it and put it down at the bottom here, that's not a square anymore. So what in the world am I supposed to do when I have an odd number like this, where I can't cut it in half nicely? Well, that's what I want to address. So here's what you just saw. The big conundrum is, what do you do with this extra one? Now, with the physical tiles, I can't take the tile and snap it in half, but that's actually what we do. We're going to take that tile and we're going to cut it into 2 halves. We're going to take half of it and put it here. We're going to take the other half and put it down below here. Let's see. Put it down below right here. So when I'm looking at this in terms of the length, right, we've always put an outline around this like this. We're still going to do the same exact thing. We've drawn these lines like this. And then we said we would ask, how long is this length here? Well, that's x long. How long is this? This is x long. This is +1, this is +1, and this is +1/2. So this is 2.5, but I'm going to write that as +5/2. And I'm going to do that because I want it to tie back in to this value here, as we've done with all of the other problems. And then same thing here. This is +1, this is +1, this is +1/2. So that's 2.5, but I'm going to write it as +5/2. So I'm going to make this square. This square is going to be x plus 5/2. Now remember, when we do this work, we're always interested in what's going on in here. So let me extend these lines like this. And here's what I hope that you notice. Do you see that this is a complete square? It's 1 by 1. This is a complete square. This is a complete square, and this is a complete square. So this is a +1, an area of +1. So is this one, so is this one, so is this one. But these over on the side, this one here, this one here, this one here, and this one here, those are not +1. Those are smaller. Remember, we get these areas by multiplying. So +1 times +1 is +1. So what would this be? Well, that looks like it's +1 times +1/2. So this is +1/2 right here. And so is this one. And so is this one. And so is this one. Right? We're multiplying 1/2 times 1. 1/2 times 1. And then we have one more piece left over. This piece in the corner here, that's the smallest of all the pieces. That one is going to be 1/2 times 1/2, which is positive 1/4. Now I made these pieces here to fit in, right? These are going to be all positive. So here are those positive 4. Here is the positive 1/2 in the vertical orientation. Here's the positive 1/2 in the horizontal orientation. And there's that 1/4. Do you see how that all fits in and makes our square? Now, as we've said before, we have all these leftovers, right? So this is our square, but over here, these are the leftovers. And so let's see how much we have left over. So we have this -1. We have this here, which is -4. This is 1/2 and 1/2, so that's -1. This is 1/2 and 1/2, so that's -1. And then that's 1/4. So let's add all that together. So we have -1 and -4, which is -5, -6, -7, and 1/4. So I'm going to write this as x plus 5/2 squared minus, again, 1, 2, 3, 4, 5, 6, 7, and 1/4. And so I would probably write this. I'm not going to write this as a mixed number. Normally, when you see this, you're going to end up writing it like this. 7 times 4 is 28, plus 1 is 29/4. Okay, so that's what I think my answer is. I'm thinking that this amount of area, this original amount I started with, I think it can be rewritten like this. But I'm going to do it symbolically to verify this. Okay, I want to do it symbolically to show you that it does equal that. So symbolically, we normally took the x squared plus the 5x, and then we added something, and then -1, and then we subtracted something. These two things that I'm adding and subtracting, this amount here and this amount here, remember that these made our zeros. So when we created this, we found that these were the dimensions. And so in order to get this amount, which is the amount we're usually, that we care about, we're going to take positive 5/2 and square it. Well, positive 5 times 5 is 25. 2 times 2 is 4. So this amount down here is positive 25/4. And then this is the negative version of that. And then this is that -1 that we had from the very beginning. So let's do it. Let's take the number of tiles, which is positive 5. Let's cut them in half, which gives me positive 5/2. Let's square it, because positive 5/2 times positive 5/2 gives us this amount, which is 5/2 squared, or 25/4. And then I'm going to subtract that same amount, because remember, these have to zero out. I have to be left with the exact same amount of area that I started with. Okay, that was that original problem. Now, we've said several times that these three here create our square. So let me write it like this. Actually, we can just go right to our squares here. So what we said was, in order to create our square, we take the terms that are being squared and we place them in here, in these parentheses. And that makes sense because that's exactly what I have here and here. Then I have the leftovers. So this is our square, and these here are the leftovers. So I have the -1, subtract, and we said this was 25/4. Remember, when you add or subtract fractions, you have to have a common denominator. So I'm going to rewrite this in terms of fourths. So that's going to be 4/4. And so now I have my common denominator, and this becomes 29/4. And that is good to see because that's exactly what we had up here, right? That's exactly what we wrote. So that problem is correct. Now, here's what I want you to notice. Remember that we took you through easier models first. We used the algebra tiles. Everything always worked out very nicely. And so using the algebra tiles was awesome. It let you see the why. What am I doing? Why am I doing it? All of that is explained. And then we started to do the algebra tile problem next to the symbolic manipulation. And you saw that every piece that is in the symbolic manipulation has a purpose. It has a counterpart over here in the algebra tile section. But now we get to this problem where we had 5 of those X tiles, and all of a sudden it becomes impossible to do it with the tiles. You can draw it out, which is a good option, but I can't split a tile in half in Mathagon. So it's kind of nice to start moving from that very concrete algebra tile model over to the more abstract symbolic model. If you get the hang of this, there is no need to create the algebra tile model. Okay, it served its purpose, and now we can start moving in this direction where I can just do this symbolic portion instead. Okay, so that's how we move forward. Okay, we keep going, move from the concrete to the more abstract.